So in this video, we're just going to look at three different types of special right triangles and how we get them from other shapes. For example, a square can help me get a special right triangle because we have to recall what we remember about a square. In a square, we know the properties from our quadrilaterals unit is that all four sides are congruent and that all four sides are perpendicular. So when I talk about the diagonal of a square, when I do this and I form a diagonal, I am creating two 45, 45, 90 triangles. This is a 45, 45, 90 triangle. So when I'm looking at this just a little bit bigger, I'm going to kind of pull this out separate. This is what I'm looking at here. And I know it's 45, 45, 90. I know that this is my diagonal and it is 8 centimeters. Now our special right triangles, I'm not going to draw them out separately here. These are the ones that you need to know, you need to remember. If it's 45, 45, 90, I know that these side lengths are the same. So I just really need to find one of them. I don't know what the side lengths are, but I know that they are in a ratio. Since it's 45, 45, 90, the legs are over 1, or a side length of 1. They correspond to a side length of 1, and the hypotenuse corresponds to a side length of square root of 2. So now I have my fraction with all numbers, my ratio with my variable. I can set up a proportion. X over 1 equals 8 divided by the square root of 2. Cross multiply. X square roots of 2 equals 8. Divide both sides by the square root of 2. And I'm just kind of going pretty backwards here. I'm showing a lot of steps that aren't necessary. But I get 8 equals, or X equals 8 over square root 2. This is a good review of rationalize your denominator. We cannot leave this as my answer. So I have to multiply by 1 in a very specific manner. Square root 2 over square root 2. Not just square root 2. That's not multiplying by 1. You need to show both. That way, the numerator becomes 8 square root 2. The denominator, this becomes square root of 4, but the square root of 4 is 2. Now I can simplify to 4 square roots of 2. But be careful, because the question's asking to find the perimeter of the square. What we just found is one side length. I just found that this is 4 square roots of 2, which means this is 4 square roots of 2, this is 4 square roots of 2, and this is 4 square roots of 2. So the perimeter would be 4 times this. 4 times 4 square roots of 2, 16 square root 2, and we are dealing with centimeters. That's the perimeter. Equilateral triangles. Again, remember back to first semester what an equilateral triangle is. Most specifically, it's equiangular. So I know that these are all 60-degree angles. It's also equilateral, meaning all the sides are congruent. Both of those are really important here, because when I tell you it has a perimeter of 24 inches, each side isn't 24. That's the full perimeter. I take that and divide it by 3. That makes each side 8 inches. Second, if they want the altitude from A, so if I call this A, B, and C, and it really doesn't matter where I put A, since all sides are equal and all angles are equal. Altitude, recall, starts at your vertex and is perpendicular to the opposite side. That's my altitude. So what I've just created here is a 30, 60, 90 triangle. Altitude means 90, and I already have that 60, so I am looking at a side length of 8 here. That's my 60-degree angle. That's my right angle. we want to know what the length of that is. That's the altitude. So I need my 30, 60, 90 relationships. Across from 30 is a side length of 1. That doesn't help me too much here. Across from 90 corresponds to 2, so I put 8 over 2. Across from 60 corresponds to square root of 3, so my altitude goes over square root of 3. There's my proportion. The altitude over the square root of 3 equals 8 over 2, and I could simplify that if I want. Cross multiply, 2 times the altitude equals 8 square roots of 3. The altitude is equal to 4 square root of 3 inches. Again, that comes from knowing the properties. Last but not least in this video is two different triangles where we have triangles that have a shared side, a reflexive side. And in this case, we have two different special right triangles. I start with a 30, 60, 90 triangle, and then I have a 45, 45, 90. I know it's 45, 45 because it's right and isosceles. So I kind of want to treat this separately. And if you look at them separately, I'm going to scroll down so I have more space to use here. I have this triangle, a side length of 10. There's a right angle, there's my 60, there's my 30. I don't know anything else. And then I have this triangle. That's my x, that's my y, and that's my z. That's my x in this, but I can't use anything in my 45, 45, 90 triangle yet. So you have to start with the 30, 60, 90 triangle, because that has a side length we know, and it has an x. You have to start there then. So across from my 90 in a 30, 60, 90 corresponds to 2. Across from my 60 corresponds to square root of 3. There's my proportion. X over square root 3 equals 10 over 2. So 2x equals 10 square roots of 3. When I divide by 2 on both sides, x is 5 square roots of 3. That's hugely helpful because I now finally have something that I can use over here. I know that this is 5 square roots of 3. That's the side that they both share right here. So once I find what x is, I can use that. Now I can use my 45, 45, 90 relationships. That's over 1, that's over 1, that's over square root 2. These are congruent. They're marked congruent. It's isosceles. Oh, I totally messed this up. That's a W. Should have found that too. And we will. X is 5 square roots of 3. We'll go back to W. But y is 5 square roots of 3. Those are congruent. Then z over square root 2 equals 5 square root 3 over 1. Z is equal to 5 square root. 2 times 3 is 6. That does not simplify. I get 5 square roots of 6. Now, W is over 1, so I do need that. And I would set up W over 1 equals 10 over 2, 2W equals 10, and W equals 5. There's all of my sides. Be prepared for problems like any of these on tests and quizzes, and check in your homework packet as well.